So the purpose of this talk is to, give you a description, introduction to this notion of template games. So there is a general purpose of logic today, which is to understand logic in space and time. So you can imagine here Eloise and Abelard discussing together. And of course, there is a dialogue between them. And we want to understand, in a way, how this process works. You know, when two people interact and try to convince one another that they are correct. And using ideas coming ideally maybe from physics or the intuition that there is a space and time of logic and that we would like to understand it better. So, indeed, if we think about a dialogue, there is combination in space, but also synchronization in time. And so this is nicely described using game semantics and ideas from linear logic that I will explain now, okay? So the starting point of game semantics is that every formula initiates a dialogue where the proponent tries to convince the opponent and the opponent tries to convince, to refute the proponent. And so a typical example is this formula here, which says that, so imagine that A means that, okay, so maybe just let me show you the proof first. Okay, it's a very simple proof in classical logic of a statement, and the statement says that, maybe I will write it here, okay, that, okay, if you say A of X is drinking, so if you enter into a bar, okay, there is a very sober customer, okay, exists Y, such that if Y drinks, all the other customers in the bar are drinking, okay? This is slightly maybe counterintuitive, but this is true in classical logic. And if you try to understand the winning strategy behind the proof I've just shown you, so this is the proof here, formal, and the winning strategy goes like this. So the prover picks randomly a customer in the cafe, and then the refutator contradicts prover by exhibiting a customer X, which is not drinking, while Y is drinking. And then because the logic is classical, okay, and not constructive, the prover is allowed to pick as new witness the witness given by the refutation. And in that way, in the end, wins. Okay, so there is some kind of interaction here, which we would like to analyze using, these tools.
The bar is not empty, yeah?
Yes, it's very important that the bar is not empty. Yes, exactly. And in fact, this is interesting that in the tradition of formal logic, bars are not empty. Yeah. So, if you take a set or of possible witnesses, there is at least one element. Yes, indeed. Yeah. Yeah. But you see,
there's only one person in bar.
If there is one, it's automatically. Yes. yeah. The point is, another way to say that is a proof in. A formula in classical logic is either true or as a counterexample. This is what is behind that. Okay. And the point is that so in a way, it's true as long a counterexample is found. That's the idea behind this little strategy. So in order to, so this is just like words and some kind of description of a process, but we want to have a more algebraic view of it. And so a good starting point is linear logic, which is based on the duality. So imagine that you have the chess here game. And so the idea is that if A is that, if the formula A corresponds to that game, not A corresponds to the same game, but where the opponent starts. Okay, so you just, switch the point of view. Okay, so negation here is just switching the point of view on the current formula. And so in particular, double negation of a game, a formula, is the same as the original formula because you switch twice. Okay. Then there are basic constructors, which are connectives, which are really inspired by linear algebra. So there is the plus here, where, so the idea is that if you have two games, you will let proponents select a board, and then we will play on that board and never play on the other one. Okay, so only play on one board. And this is a form of constructive disjunction. Okay, here, so proponent will be like typically a proof, and it selects, it says, okay, A or B, it says A, okay, and it carries on here. And the dual, I mean, so there is a dual is just the situation where opponent selects the board, not proponent. Okay, and it's just the De Morgan dual. It's just plus, but seen from the point of view of the opponent. Then there is a tensor product. So the tensor product is interesting. Is the two games are played in parallel, but only opponent is allowed to switch board. Okay, so only opponent can switch board. Otherwise, I mean, the two games are played in parallel. And you can see it as a form of classical conjunction. And now, by duality, there is a par where this is player which is allowed to switch board, but not opponent. And this can be seen as a form of classical disjunction. And to see why, I mean, there is a beautiful proof that A or not A. Okay, so this is this little or. You can think of a disjunction. So you should play that game where you are here playing on that board. So you are A, and here you are not A. You are just the same board, but reversed. Okay. So how do you win? I mean, how do you win that game? So the purpose is to win on, because it's a disjunction, you need to win only on one of the two boards. So, I mean, when you play against your contradictor, I mean, typically, in fact, you will play against a pair of contradictors, very good chess players, and you need to win, okay? And so it seems impossible. But in fact, there is a very simple and pretty stupid strategy, which is to do a copycat, to wait, I mean, to let Korchnoi play here, and then because you can switch board, you play exactly the same move here, and then Karpov will answer, and you move, I mean, switch board and play like Karpov did, so that Korchnoi believes he plays against Karpov, and Karpov believes he plays against Korchnoi. In the end, maybe Karpov is in a good day and wins, okay? So clearly you lose on that board, but you win against Korchnoi. And so because it's a disjunction, what matters is that you win one of the two games. Okay. So this...
Draw at chess.
Hmm?
We have draw at chess.
Yes, so if there is a... I mean, yeah. So here we will I mean, allow ourselves to say that there is no draw, yeah. Okay. So, you know, there are very basic ideas, but what is nice with the approach is that it's game theory, if you like, okay, very basic game theory, but at the same time we will see it can be turned into a real algebra, okay.
The sums also this like Conway group of games.
Yes, it's very much inspired by Conway. Yes, it's exactly like indeed. And so, and also there is, and we will, I mean, we'll see in the models. In fact, the sum is like. You know, the sum of vector spaces. The tensor is like tensor of vector spaces. And here there is another, there is a modality, which is something like the free commutative coalgebra construction, where you let opponent replay, I mean, as many copies as necessary to beat proponent. So the idea is that opponent will be allowed to open new copies and again and again and again as required. And this coalgebraic construction on games, in fact, explains a lot. In particular, it can be understood as some kind of backtracking where you're allowed to replay a game. And this is exactly what we saw originally with the drinker formula. The strategy was allowed, I mean, was losing on one board and reopening a board and then winning with the information gained on the first one. Okay. So now I will give you a very okay, maybe I just mentioned that we have, like, there are nice equations, like, for instance, I mean, tensor and okay. So, I mean, there is a nice algebra behind the scene. But what I want to stress here, I mean, and to focus on, is how these games can be described in the language of category theory. Okay, and in fact, we see it's not very far from the talk that Nick gave. And because it's about composing strategies, okay? Instead of composing rewrite rules, it's about composing strategies, winning strategies, okay? So the idea is extremely simple. So we will use a category. Okay, so the idea is to define games as categories, but labeled categories. So here we use that very simple game. Sorry, this very simple category with two objects and freely generated by these two edges. So typically, I mean, the maps from plus to minus are O or OPO, OPO, and the idea is that this describes some kind of this describes some kind of polarity on games where this is, I mean, opponent playing and then player playing and then opponent and so on. So this is some kind of labeling. And so the category will play a very important role in that talk. And so now a game will be simply defined as a category equipped with a functor to that category that I will call the template of games. Okay, so it's just, if you like, a labeling or a coloring of the category A. So if you think about it now, I mean, you should think of the objects of the category A as positions and the morphisms as trajectories. And you can think of the category A as an unlabeled transition system. Okay. And now the polarity functor will assign a polarity plus or minus to every position of the game, so every object of the category. And the position is called player when it's mapped to plus, and opponent when it's mapped to minus. And then an opponent move is simply a morphism in the category A, or a trajectory, which is mapped to O. And similarly for player move, it's a trajectory which is mapped to P. And now a silent move is a trajectory mapped to the identity. Okay, that's okay. So now, in that way, a category is, I mean, labeled in that way. For instance, chess. You could imagine that chess is described in that way. Okay, so where opponent and player are the two labels for moves of opponent and player moves. Okay, black and white. Okay, so now. This is good. This is good for games. But now we want to define strategies in the same way. And so we introduce the template of strategies. So it's just that little category here. Again, so it's a category with three objects and freely generated by this graph, okay, with 4 edges. And so the intuition is that we want to describe a strategy that plays between two games. Okay. So how do we do that? Okay, so well, if it plays between the two games, it should be able to play. I mean, there should be 4 kind of moves: the opponent and player moves here in the source game, and the opponent and player move on the target game. Okay, so and this is what this template here, this category describes here. So I mean, each of the edges here of the generating graph can be depicted like this. We will see there is a little picture like this. So that, for instance, this sequence OT, PS, OS, PT can be represented like this. This is OT, PS, OS, PT. And the idea is that we want to describe the flow of an opponent move played in B, in the target, then transported to a player move in S, in the source, then an opponent move played in the source, and then transported to the target as a player move. This is what we want to describe using these 4 edges. And in fact, okay, so there is a way to map this category we've just described here. So this one. So to the template of game by a source and a target. So the definition is, I mean, all this. This category is freely generated, so it's quite easy to define functors. But the way, in picture, the idea is that OT, so this situation here where we see the flow of the strategy, so some kind of particle going from here to here. So if we look at the source, we will get here. And if we look at the target, we will get that. Okay. Just by mapping, typically OT is mapped to identity here and O here and so on. So remember, this is just the pictures for the category, the template of game with opponent and player edges. Okay. So now we define a strategy as just a span of functors. Okay. So the idea is that we have positions in A, positions in B. So every position in the strategy should be able to be mapped to a position in A and in B. But also we want a scheduling functor, which will be a functor from S, the support of the strategy, to that category, the template of game. And we ask that this diagram commutes. So let's try and understand what it means. So here we have the support. Okay, so there are the states, the internal states of the strategy. And now they can be mapped to A and B. And what we want is that when there is some scheduling of the strategy, okay, so we imagine that there is a trajectory here, inside the support. So this is some kind, in your brain, you'll just have this trajectory. Then it's mapped to A and B, and you want that this description of the scheduling of the internal, the strategy internally is mapped here properly to the same scheduling of A and B. Okay, so that's why these maps are important here. Okay, so this is some kind of requirement, and so now a typical example is, imagine you have two games A and B with two moves, and so there is a player move here. So the environment asks a question, for instance, to B. The strategy doesn't know how to answer, so it will ask the question to A. There will be an answer by the opponent but playing on A, and the answer will be transmitted to B. Okay, this kind of situation, okay, here will be described in that way. So it will be just a sequence of. So here now we are looking at a morphism in the support of the strategy, but we are looking also at the labeling, and so the labeling tells us what each move is doing, where it plays, if you like. So this is you remember I mentioned space and time. This is this is time, clearly, but this is space, okay? It describes where the things are happening. And okay, now a simulation between strategies is simply a map of span. So okay, so we saw that a strategy is a span, okay? And so now between two strategies we can define a simulation is just a map of span, just compatible with the scheduling. Okay. Now, this defines for two games A and B a category of strategies between A and B, and the simulations are the maps between the strategies. Good. That's good, okay? But we want, of course, to go one step further and to construct a bi-category of games. So what it means is, it's not, so really is that we want to turn this family of categories of strategies and simulations into a bi-category. But okay, so the word bi-category is like a weak two category. And really what it means, okay, is that given a strategy between A and B and a strategy between B and C, we want to be able to compose them to get a strategy between A and C. So, okay, imagine we are here. Okay, sigma plays between the games A and B. Tau plays between the games B and C, and we want to glue them, to merge them in order to obtain a strategy from A to C. And so, really the purpose is to compose strategies. So in that sense, it's not very far from what Nicolas was speaking about a bit earlier. So instead of composing rules, or more precisely instances of rewrite rules, we want to compose strategies. And we will do that by, so if we look at the situation, it's like this. We have one strategy from A to B described as a span, but the span, also equipped with some template, okay, describing how each morphism, okay, so A, S, and B are categories, so it's a span of categories here, okay, here. And this is another span of categories, and these are describing exactly, where, each of the trajectories in S are, where each of the trajectory in S is precisely acting on A and B. Okay, so that's the scheduling, if you like, of the trajectories in S. Similarly for T, so we have sigma, this is the strategy sigma, this is the strategy tau, and we want to compose them. So clearly a temptation, and this is what we are going to do, is to compute, to compose spans using the usual definition by a pullback here. So the pullback is produit fibré. Okay, so it's a way to compose spans. And the idea is that if you have an internal state here connecting positions in A and B, and another internal state connecting positions in B and C, you want just to do some kind of relational composition using this pullback. The challenge is to understand, okay, how this pullback will be scheduled itself. And so that's where some interesting structure is appearing. So we will look at the composite of these two spans on templates. Okay, so let's do that and compute the pullback here. Before computing the pullback here, let's compute the pullback here. Okay, let's compose these two spans. So we get something here. And a very interesting and slightly unexpected thing is that this pullback, which is computed in cat, okay, so in the category of categories, happens to be a freely generated category. So we can easily describe it. So it has 4 positions, okay, and it's freely generated by these 6 edges. Okay, and if we look at the edges, we see that they're describing, in fact, what's going on between the strategies. So it's about, 2 people meeting and interacting together. And so, in fact, each of these 6 edges can be described in that way. So you should think really, of particles exchanged between the strategy sigma and tau. So what can happen here, for instance, is that, so when opponent plays, so this opponent starts here, for instance, on the external game, and this will be described in that way, by this little step. But then there is some, exchange of information between the strategies, which will be described by, in fact, these 2 edges here, where you see, if you like, the particle going from tau to sigma or from sigma to tau. So this is a place where information is exchanged. And here, this is the same as here, but on the left. Okay. And so now, for instance, typical interaction CBAA-BC will look like this. So you have just this sequence of 6 edges here. Okay, so we go from here to here. And where you see that some information which was on the right, so this is played by tau, and this is played by sigma, and the information here flows from tau to sigma and from sigma to tau. So here I don't speak about sigma and tau, I only speak about the templates. So I just describe how the information is synchronized. And so really the fundamental idea here is that this pullback computes a synchronization of the 2 strategies, but the shape of the synchronization is very easy to analyze because it's just described by this freely generated category. Okay. So now, if we think maybe more as maybe like very basic physics, the idea is, in fact, this pullback we've constructed lives inside the Cartesian product of strat and strat. So what this means is that, in fact, we have 2 strategies, sigma and tau, and they could evolve in a completely independent way. But now we want to constrain them so that they behave in the same way on the interface B. Okay. And when we do that, in fact, okay, we realize, so these are all the possible, so these are the, each strategy can have, can be in 3 states. So if we take the pair of strategies, we get 9 states. And now if we force the 2 internal states to be the same, we get 4 states, which are precisely, describing the 4 states of the pullback here. Okay, so if we fatten a little bit, we get exactly the strategy, the category that we had here. And so, really what it describes is how, this template of interactions describes how the 2 strategies synchronize. And so what we get here, moreover, what we observe, moreover, is that this template of interactions has a functor into the template of strategies, which is height, okay, and you can also define very easily. And pictorially is like this. So these are the different, the 6 possible edges generating your template of interactions. And when you hide, it's just that you hide what's going on inside. Okay, so the OP and PO, which are the interactive edges, the edges of interaction, are mapped to the identity. Okay, and so this, in fact, enables us to compose strategies in that way. So we just take the pullback of S and T, but now this pullback is mapped to the pullback of the template of strategies, which is the template of interactions, and we use this functor to map back. To map this now. So these are the internal states of the composite to the template of strategies. Okay, and this is the picture we use to compose strategies. And this implements the slogan that composition is synchronization, which is computing the pullback plus hiding. Similarly, for the identity strategy, we can just observe that the template of game has a map to the template of strategies, and which duplicates, in fact, the moves in two. And so you can see what it does here. So one edge becomes a path of length 2, and one edge here becomes a path of length 2. But the point is that in that way we can define the the identity strategy just using a very basic construction on spans. Okay. So okay, and so this is the picture, which is really the same picture as for composition but for identity. Okay, and so in that way we get a composition of strategies. And if we think more, maybe abstractly, conceptually about what is going on, we realize, in fact, that the reason why composition works is that the categories that we've just defined here, so the template of game, the template of strategies, the template of interaction, define an internal category in CAT. Okay? And so an internal category in CAT is, okay, so it's a formal definition of some structure, okay? But in fact, another way to describe it is to say that it's a double category. So all the pictures I've shown you earlier are also instances, so in particular this one, okay, when we were looking at this, instances of what Nicolas showed you earlier with double categories that we can compose. We can compose these schedulings together in order to describe the way strategies interact. Okay, and so this is really the secret, if you like, structure behind the scene here. Okay, then, if you want to, so we get that games now defines a by-category. So we have a by-category with objects are games, maps are strategies, and two cells are the simulations. Okay, but we also, in fact, show that this category, this by-category is symmetric monoidal, and in fact, star autonomous, which means that it has very strong dualities. And so it's interesting to note that the way all these results are obtained is always the same fundamentally. It's about constructing a new internal category for each of the connectives. So for instance, there is an internal category of tensorial schedules, so if you like a double category, and which is moreover equipped with internal functors into here it's the pair of internal categories, and here it's just the internal category. So you can think of them as functors between double categories, okay, that I call pick and pins, and I will explain why. Here. Similarly for the par, okay, so, and similarly for the up, okay, so which are the basic constructions, remember, in games. We had a tensor, we had a par, and we had a duality, which is up here. And so it's always based on some basic, operations of pull and push that I described here. But just to show you the template of tensorial schedules, so it's just that little category with three, freely generated by that graph with three objects. Okay, but what is interesting is that these three positions, objects, they describe, in fact, what are the allowed polarities in each game. So it's, if you like, it's a kind of algebra of how you can combine games. And in particular, here, you're not allowed to, to be in a position of polarity minus, minus. Okay, so you only want plus, 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 minus, or minus, plus. Okay. And so the intuition is that each player plays only in one step and not 2 steps in a row. Okay. And so this is the now the template of strategies, and then we can analyze it. But the point is that, in fact, once we've constructed this template of tensorial schedules, we can analyze how it's mapped into these 2 other templates. Here, the peak internal functor picks the positions which are allowed, okay, in the Cartesian product, in the product of 2 games. Okay, so this position is, this polarity is rejected, and the pins functor does the job that says that when we have this kind of polarity, this one should be considered as positive, and these 2 ones should be considered as negative in the resulting game A tensor B. Okay, and so in the end, just to show you the picture, if we want to construct the game A tensor B, okay, we just do that. We take the Cartesian product of the categories A and B. We take a pullback on this template here that picks the good polarities, and then we post-compose to get this lambda A tensor B, which is what we wanted, which is the polarity of each position and move in that game. Okay, but you see it's really a pull and a push construction typically in a in a bifibration, in the Grothendieck bifibration. We can do the same for the par, okay? And just to show you something which is I think interesting. So from an algebraic point of view, is that the main ingredient of linear logic is this distributivity law. So this is a tensor, this is the cotensor, the dual, and there is this map here. And one, real difficulty in game semantics was to describe this phenomenon here, that we can take a tensor and distribute it inside the par. Okay. And this is where template games are very useful, because in fact, we can really analyze, we can construct a strategy, a span, between a tensor, these 2 games, okay, or category, games, just by looking at the templates and analyze very precisely what are the synchronizations involved, okay? And in fact, we realized that, there are very deep structural reasons why this law makes sense in linear logic. Okay, and maybe a word about the exponential modality, the way it's handled here. So I said that it's a co-algebraic construction on games, but in fact, one way to perform it in the case of categories, because we are working with spans, we can just construct the free symmetric monoidal category, which is an algebraic construction, not a co-algebraic construction. So if you like, it's really like the free, like the symmetric algebra, but for categories. So it takes a category C and turns it into this category with objects are words of objects of C. And this defines a monad, which happens to transport the polarities, the templates, into new templates. Yes, the reason is that, technically it's a Cartesian monad, so it will turn internal categories into internal categories. And then it's possible just to define a new template by rejecting. Okay, so here we have sim of that. There are just words, sign words of plus and minus. And the idea is that the template of the exponential will just be the subcategory restricted to only objects of the form plus, 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 or objects where there is only one negative polarity. And this is designed to describe the fact that opponent and player play, one after the other, and so when opponent plays, he adds a minus. When player plays, it turns the minus into a plus. So you never go into words where several minus could appear. Okay, so this is the sequentiality, if you like, or yes, the two-player aspect, alternated aspect of these strategies. Okay, and then you can really redo everything, and okay, it's just the same constructions that you apply, and show that this category of that by category defines a model of, in fact, linear logic, but there is an extension, very beautiful extension, to do some differential calculus. So, and the point, interestingly, is that in order to get a model, one realizes that one is to apply ideas from, I mean, homotopy theory. Okay, they are very limited, but one needs to work in the Quillen category of, I mean, so-called the natural Quillen model on cat, and really work up to equivalence of categories. So, and I think, in fact, the word homotopy makes sense here, and that in other kind of models where we work instead of cat in other kind of structures, homotopy should play an important role here. Okay, so I mean, imagine we want to work, for instance, with infinity structures. Or okay. So anyway, so this is the conclusion. So I've shown how to play games on categories with the notion of synchronous. I mean, how to synchronize strategies in space and time. Then, in fact, it's possible also to play on two categories with an asynchronous notion of composition. And interestingly, when we work with two categories, we need to use the gray tensor product of categories instead of, I mean, so and in particular, it has a lot to do with gray coalgebras or comonoids instead of, and bicomodules instead of spans. So in fact, there are many different notions of templates that can be used. There is a nice connection between linear logic and ideas from homotopy theory, and this can be adapted to many other logics, in particular logics that are used for verification of programs. And so the idea is that you can connect in that way very logical structures with very like imperative or more computational structures. Okay, thanks. Yeah.
Questions?
Ah.
Yes. Comment mathématiquement sont modifiés tes objets si jamais on essaye d'introduire le concept de match nul, justement?
Okay, so okay, so I mean that was the point is, you know, everything is done here to allow different kinds of games, yes, and so the intuition is to work in a very minimal framework where we have, and in fact, it's inspired from, you know, like graph theory. Okay, so here a game is a category. Could be a two category, it could be other structures, okay, equipped with a labeling. And so everything is in the labeling. So here, for instance, we could imagine to have, for instance, winning positions and draws. You know, as a matter of fact, I don't speak about winning here, yes? If you notice, I just speak about the scheduling. How two people will, interact together. If you ask me a question, I will answer. Okay, and this will be synchronization in space. Yes, and so if you ask, but it's not about winning conditions. If we want to have winning conditions, okay, we say there are two ways. Okay, just to, so one is to maybe put maybe some extra notions of, you know, polarities. Yes, like for instance, there would be some instead of saying, okay, these are player and opponent positions. So player position means player is happy. It's content, okay? Here, so there is a little bit of winning condition here, but really we could have really winning states or winning positions and on both sides. And then a position will be mapped and say, okay, here is, you see, I mean, this is one way. The other would be to say that, in fact, we want to have some orthogonality condition on the strategies. So this is something that I like also very much. So in the models of linear logic, very often people look at some kind of so it's called orthogonality. It means that a player and I mean the strategy and the counter strategy will behave well with respect to one another. So I mean there could be different ways. But what I want to stress is that this template is very general, and you could have draws, for instance, if you want. Yeah. Okay.
Is any sense to consider games on n category?
Sorry?
To consider not 2 category but n category.
Yes, yes. So that's a motivation. So in fact, yes, the interesting thing is that maybe I can show you very briefly. Yes, it's a good question because in fact these are the things.
I was not sure what was the question. It was
so it's about moving from categories to n categories or other higher dimensional structures. So just to show you that so n category, I mean, so n categories or n dimensional, automata, for instance, they are important for describing synchronization, for instance, between n different players and different shapes of synchronization. And so already, it's possible to extend what I'm doing here, and instead of playing on categories, I mean, typically generated by a graph, working on 2 categories generated by some kind of asynchronous graph. So it's a graph where you can permute like Mazurkiewicz traces. And just to show you maybe a picture. So the idea is that then you can look at that kind of shape where you can permute, for instance, 3 moves into 3 moves by different ways. And so build some kind of space of trajectories which is more sophisticated. So I've worked on the 2-dimensional aspect, but n-dimensional is possible. What is interesting is that in order to work with this structure, I need to use the gray tensor product, so the gray tensor product of 2 categories. And so and I need to replace, so instead of having span, like, I've shown you, I have a span like this. This was the shape for categories. Okay, for 2 categories, but then for n, I think. Okay, it's replaced. Okay, it's replaced by something which is in fact a bicomodule. And so in the end, instead of working with spans and composition of spans, this becomes composition of bicomodules. And so composition is by equalizer. So what I mean is that this is just composition of bimodules, but dual. Yes, and it's interesting that in fact there is a very unexpected connection between bicomodules on the gray tensor product and games. Okay.
Okay, so here you have Jan-Baxter equation, then
Yes.
you have the Zamalchikov equation.
Yes. So you said, yeah.
Zamalchikov. So because
Yes.
this is higher,
Yeah.
it works by Voevodsky and
Exactly. So this is the Young-Baxter that I need, in fact, to do my work. But I would like indeed to have higher structures to integrate new equations and look at what they mean from this point of view. Yeah. Okay.
But you can interpret this with also Jacobi identity.
Yes. So
because if the face is uv minus vu, this gives the Jacobi identity.
Yes, so it's something we like to discuss with Gérard. There is some Jacobi identity in this Young-Baxter equation, because so I think it's interesting to look at the kind of higher n-dimensional spaces that you can construct, and then the interactions and the way you can make different systems interact together. Really it's about how you merge different string diagrams with dualities together in some external way. Because in the end, we construct, in fact, this could be adapted to do knot theory, for instance, in some way. One needs to think about it, but this is the kind of directions that one would like to explore. Yeah. Yeah. Thanks.